Hello, my name is Ignacio Cuiral, and I'm going to be talking about Multiscale Laplacian-based fast marching method for shape control. This is the structure of the presentation. I'm going to begin with the problem statement, what is shape control and what's our problem setup. Then I will summarize our proposal, and I will introduce multiscale Laplacian descriptors and how we use them to perform an elastic contour matching based on the fast marching method. Then I will explain our control strategy, and I will also explain our simulation results. So the problem statement, what is shape control? So we're trying to solve the problem of bringing a deformable object into a desired target shape. We're assuming the information we have from the object is provided by an RGBD sensor, in this case, for instance, an RGBD camera. And this means the contour of the object is defined by discrete points, and they are homogeneously distributed. There is gamma G grippers gripping the object all around its contour in different points, and each of the discrete points of the contour has its own reference frame, as you can see here, with the y component pointing upwards, the x component being tangent, and the z component being perpendicular to the other two. So this is our problem setup and our problem definition, but we also are making some assumptions. We are assuming the objects are going to be a large strain. This means they're not deforming, for instance, like a gum. I'm also assuming it's going to be textureless. This means I cannot rely on visual descriptors for any kind of matching. And also, we're making things a little bit realistic when it comes to defining the number of grippers we can use. In a real setup or in a real workspace, more than even five robots working in the same workspace is going to be quite difficult or even impossible. It's very hard to plan avoiding collisions. So we're assuming we're using a reduced number of grippers. We don't want to depend on learning or initialization, or we don't want to be parameter dependent. I don't need to know the physical properties of the object, its density, its elasticity, and also I don't want to rely on learning. So this is our proposal setup and our assumptions. What's our scheme? Our proposal scheme is the following. We've got a target shape. We retrieve the current shape using the RGBD sensor. We perform an elastic matching using fast matching method between both shapes. And then we perform a procrustes optimization between the matched points. This means we're reducing the distance between matched points in a global manner. And also, after this, we use our control strategy in order to define these U sub G actions for each one of the grippers. What is a multiscale Laplacian descriptor? So each shape, even if it's a current or target shape, is defined by the set of discrete points. For each one of these discrete points, which are homogeneously distributed, I can perform or compute the random walk Laplacian. What's interesting is we're going to do it at several scales of neighborness. For instance, in this case, we are choosing this lambda scale. Each lambda corresponds to a neighboring scale, and the set of scales is evenly distributed, meaning that the distance step between scales is the same for all of them. It's also interesting to mention that this neighborness is defined topologically, meaning it's always to be along the contour. The distance is going to be topological. For each of these Laplacian coordinates I compute, I can extract the local components of the contour point. If I arrange the local components separately in three different surfaces, x, y, and z, I obtain what we call the multiscale Laplacian descriptor for a given local component. In this case, the y component, which corresponds to the normal component of the Laplacian coordinates, pointing outward, outside the contour. So here you've got a descriptor, which is for all the contour points and all the scales I'm analyzing the object. I can do the same for the target shape. Here you can see the differences. It's easy to note the two tips of this object here. This is one of them, and the other one is divided by the descriptor itself, but you could think of this descriptor as a cylinder that it closes in this point, because again, this is a closed contour. So the target shape, you can see the differences. You can see this concave curve here with negative sign, and this convex curve on the outside here, which is also longer because it has larger radius, and it has a positive sign because it's pointing outside the shape. So the elastic matching is performed using these descriptors in Forrest-Martin method. The Forrest-Martin method solves the kernel equation, which is solving the time cost of a wave propagating at point theta, bar theta, with a speed f at this point. We can define our speed function, or speed surface in this case, because it's a discrete surface, using the Laplacian descriptors, subtracting the target Laplacian descriptor to the current Laplacian descriptor for a given component. And if I combine the three components, this results on the similarity surface between current contour and target contour. Applying the Forrest-Martin method, I obtain the time cost surface, and I can perform a gradient descent from one corner to the other, and this path is going to interrelate both contours, and therefore it's going to define my elastic matching. This can be understood in a better manner if we see the comparison of the evolution of the surfaces in the deformation process. So we got the initial state with the current shape being the red bar, and the target state, which is the blue curved object. And once the red object is reaching this shape, you can see how the similarity surface pops up, or it has higher values on the diagonal. This is easier to explain if we can visualize it. So here we've got the F surface being generated by the interrelation of both descriptors. In this surface, the warmer colors represent points that are similar to each other. For instance, these two tips are very similar. But if I compare this tip to one point in the middle of this long part of the object, it's not that similar. So we see colder or darker blues. This similarity surface can be then introduced in the Forrest-Martin method, and we obtain the assignation cost surface, and performing the gradient descent, we've got then our shortest path. So if we see the animation of the wave, or in this case the front propagating along this surface, we can see how it corresponds to the assignation of points along both contours. So this is the elastic contour matching using the Forrest-Martin method. The control strategy. Okay, so we've got the reduction of the Laplacian smoothness energy by means of this energy function. Also, we've got this important constraint, which is representing the matching between contour points. So this constraint, what is actually defining is subspace of affine transformation between matched points and their corresponding local frames of reference. So within this subspace, we are reducing the Laplacian smoothness energy and defining the target position, or in this case, deriving the velocity of the creepers. So this is our control law, which makes use of the result of the minimization of the energy function. And we tested it in a simulation setup using the as read as possible deformation model, which also fits our large strain assumption. And also we defined a couple of metrics to see how this performed. One of them is the boundary error, which is the distance between matched points. We can see how it converges and how it reduces. And also we are trying to see the object deformation. So here we are visualizing how these arcs between triangles are stretching or compressing. So the ones on the positive side are stretching and the ones on the negative side are compressing. This makes sense, and it's kind of intuitive to see how if you bend a bar, the outside part is going to stretch and the inside part is going to compress. So we've got positive and negative values in this deformation. So for the results, we're going to visualize the animations. On the left top side, we can see the evolution of the speed surface, or the F surface. Here we can see the evolution of the time cost surface, and again how the gradient descent path is defined in the matching at each moment. Here we can see the current shape in red and the target shape in blue. The matching is represented by the thin gray lines. The gripper positions are going to be represented with these black circles. And there is one experiment, which is the next one, which will have a fixed gripper, which is going to be represented by the green square. So this is the basic case of I being transformed to a C. This is the same case, but with a fixed gripper. So the method seems to manage properly within this case as well. This is the opposite case of converting a C into an I. Note how the similarity surface pops up higher as both shapes resemble. Then we've got more local cases, like these triangles. In this case, note how it's really hard to get this curve here, but the method converges as well to what I would say it's a good solution. Another local deformation, in this case in several parts of the star. Again, the similarity surface pops up as the cost surface starts showing lower values. Here's another local deformation, and diagonal here is so clear because in the end both shapes look very similar. And one last case in which we try to apply this in 3D. And again, the method performs, I would say, properly. So this is it. I hope you enjoyed, and thank you very much for your attention, and goodbye.